watch it later. Good, good. So good evening, everyone. This is Sandeep here. I'm going to take you through Mahat today, and it'll be a very brief introduction on Mahat and an example of Mahat. So Mahat is basically a scalable machine learning library. And why it is called Mahat? Because Mahat is somebody who drives elephants, who rides on elephants, right? And Mahat here in this context, basically it runs on Hadoop, and it runs on Hadoop to churn a lot of data from here and there. And this is the brain, this is the brain of the whole Hadoop ecosystem. So Mahat is basically a collection of machine learning library. It's a collection of machine learning functions or library which have been fairly commoditized, meaning you do not have to program at all for Mahat. All you have to do is call these algorithm after preparing the data set. All right. So Mahat is basically a collection of machine learning library functions, or you can say Mahat is a library machine learning library which has all sorts of algorithms. Now, what is machine learning? Machine learning is a branch of artificial intelligence. It is for design and development of algorithms. Computers evolve their behavior based on empirical data. All right. So what does it mean is that given all sorts of facts, computer can automatically reach to start understanding the data. Okay. It is like if A is called B and B is called C, C is called D, and after looking at it, computer can tell that then uh, D will be called E, right? So it is automatically figuring out based on the past data that what will be the future data, right? In the most rudimentary form, plotting a graph and extrapolating a graph value is similar to prediction. Meaning, if you have got 5 points and if you draw a polynomial for these 5 points, a polynomial or a graph going through these 5 points, then you are basically predicting based on these 5 points the future values of x and y, right? So similar to that, machine learning is basically makes that whole prediction of the future not only based on the coordinates or the numbers, but based on our neural network. Okay. And you could do in AI, you could either do a predictions or learn the behavior using a statistical way, doing average computation, mean standard deviation, and all those computation, or you could use a proper neural network to neural network is nothing but a chain of lot of small units which learn. Okay. So that will be I mean will be a little huge topic to discuss. So basically based on the empirical data, computers learn and then evolve automatically. Okay. For example, if you are building example use cases are many, such as spam filter. Somebody will train that this is spam, this is not spam, this is spam, this is not spam, and based on machine learning algorithm, the computer will develop a sort of intelligence to recognize spam from non-spam. All right. Now that is machine learning. Now there are three kinds of machine learning. First is supervised learning, where supervised learning is using labeled training data to create a classifier. Classifier is something that classifies things. Okay. Classifier is something that classifies things. Okay. Exactly what we just described you are spam, right? So you know that there are so many emails in your inbox which are spam, and there are so many people who are all the time reporting spams. Based on this information, if we train our computer to recognize spam from non-spam, that is called supervised learning. All right. There could be multiple ways to do it. Multiple ways to do it, such as supervised learning can be done in a machine learning way or neural network way, or can be done in a very simple statistical way, such as you count all the words and then try to figure out what all words are common in all spams. Okay, what all words are common in all the spams, or some similar statistics. Okay, what are the plurals and synonyms, and you try to figure out the similarity between spams. But that will not be a great way to solve it, because you will be all the time figuring out new techniques to solve it. Instead of it, let it go to the machine learning algorithm and let that machine learning algorithm try to figure out by itself. Okay, so basically supervised learning is, we have already classified that this is spam, this is not spam, and let it automatically figure that out. Let it learn from there. Let it learn from your classification to further classify in future. That is supervised learning, because we are supervising it all the time in the beginning. Now there is something called unsupervised learning, using unlabeled training data to create a function that can predict output. What does it mean? It means that, okay, just give me a second. All right, now we have turned on the recording. Great. So in case of unsupervised learning, based on a lot of use already created data, it starts learning by itself. You do not train it. Okay. Semi-supervised learning is where you may or may not have the unlabeled data, and this labeling will slightly help in classification, and you may have or may not have the label. Okay. Now, now these are few applications you can now correlate. Why does machine learning matter to you? Most simple one which we will consider is recommend friends. You see, when you have a Facebook kind of application which keeps on recommending you friends, so this might be your friend, that might be your friends, right? Similarly, recommending dates, recommending products to end user, recommending dates as in, uh, I mean, automatically figuring out what are the dates which are important to you. Okay. Now, the other kind of application is that classifying content into predefined groups. Okay. You have defined three groups, say, such as travel, and such as social, such as updates, and such as critical, and then you start classifying the content or the emails into these groups. So it's a very fair application which we see in the Gmail, that is largely based on machine learning. Okay. Now, finding similar content based on object properties. Okay, people who like this product also like that product. That is finding similar content. Then identifying key topics in large collection of data. Identifying key topics meaning, given a huge article, given a huge article, can some application automatically tag it that these are the prime things that have been discussed in this particular topic, right? Or giving two news articles, can an algorithm predict that these two articles are basically saying the same things? Two news articles, right? So those are the simple examples. Then ranking search results, detecting anomalies, sentiment analysis, opinion mining, computer vision, natural language processing, then bioinformatics, speech and handwriting recognition. These are the few of the applications of machine learning. Okay. Now, what are the machine learning tools available as of now? Right. So, out of these tools, which all tools you have heard or used? Which are the tools you have used so far? Jagannath, can you see this third column, C column? Out of these tools, what are the tools you have used so far? I have heard of MATLAB. Okay. This whiteboard is basically your whiteboard, physical whiteboard, right? So when you have few lines of data, a simple whiteboard is good enough. Whiteboard everybody has used, I think, right? Great. Yep. When you have few lines of data and you want to, just project it on the screen, a whiteboard is good enough. But if you go to KBs, which means thousands of records, or maybe say, well, let's go for thousands of records. In those cases, for analysis and visualization, you will require MATLAB, Microsoft Excel, Octave, R, and you will require those kind of things for processing. Now, as the data grows from to MBs or hundreds of MBs or 300 MBs, then for analysis, you would require a little more exhaustive tools like NumPy, SciPy, and all those kind of things. These are fine when you have to churn on a single machine, your data is small enough. Now, if your data grows big into terabytes and petabytes, you might have to go for Mahout or or something which runs on Hadoop or Spark. Okay? Or maybe say we call it GraphLib. MLib we call it. MLib. All right. So let's just remove that HANA. All right. So we have got these tools. Okay. MLib is from Spark, right? So these are the tools which you use. So here we are going to discuss only Mahat today. All right. Now, so one of the examples I would like to take you through is the movie recommendations. This will actually give you a better picture. So take a case of movie reviews, right? So let's say there are two persons called Sandeep and Kumar. Sandeep likes Matrix and Casablanca, while Kumar likes Matrix and Shawshank Redemption, right? So out of these total number of three movies, they have one movie in common, right? Kumar and Sandeep. So it is highly likely they will start recommending to each other, right? So Kumar will say that, hey, you should watch Shashank Redemption, while Sandeep will say to Kumar that you should watch Casablanca. And that is what is recommendation. And that is exactly how our recommendation engine works. It finds out what is most common between two users or what is the closest two users in the set, and then start recommending the movies to each other. All right. And here, I mean, that is a very important aspect. right? So this is the this is the movie recommendation, and this is how exactly any recommendation system work. It finds out which are the users which are common to each other, and then start cross recommending people. I mean, movies which Kumar liked might Sandeep will also like, because Sandeep is very similar to Kumar. And same is the case with whatever Sandeep likes, Kumar will also like, because they have a common common set of many movies, right? That's how it works. So this was the example, and this is the example which we will take you through. Okay. Now Mahat has got some use cases, very simple use cases again. First is collaborated filtering, which is recommending users. Second is clustering, takes the whole particular items and automatically cluster similar items together, okay, and organizes them into naturally occurring groups. Then third one is classification, okay, learns from existing categorization. In clustering there is no label at all, it has to automatically figure out which are similar users to each other, most similar, and which are not similar, or which are similar products to each other, right? Classification is we have already predefined labels and we have to put these elements into buckets. We have the history of various elements who have been put into the bucket, and based on that, based on similarity between these items, you have to put them into those buckets. Buckets can be any numbers, right? Then other than that, there is a fourth kind of mining which people do is frequent item set mining, which means these four items are generally sold together. That is the frequent item set mining. Okay, so these are the four use cases on a wide label, and I mean these are the four use cases you need to work upon. All right. So Mahat is used in all these cases. Basically, all the algorithms that exist under Mahat lie in these four categories. All right. Now these are the assignments from yesterday as well as some of assignment for today. First is that import data from MySQL to Hive and back, right? Build an Uzi job for fourth problem of the session 2 assignment, that is voting problem. Okay, because that requires two map reduce jobs. So you need to build a Uzi job for this. Basically, a map reduce to two map reduce passes. Third is that go through the big data sets available at Amazon and come up with the problem you want to solve. Okay, there are many other algorithms, other data sets available. You might want to solve any of those problems. All right. So that was carried over from yesterday. Now let's start with today. All right. Now, so today we are going to further continue our Mahat discussion and then talk about few more things like Spark, Storm, and NoSQL comparison. Even if we are not able to complete it today, do not worry. We'll have our 11th session on the next week. All right, and then we will continue our discussion. Okay. Now let's go ahead. So first of all, we download these files. If you want to do it, you can download this file using wget. I have already downloaded SSH student at Hadoop. In my folder, it would already be there. Okay, here let me just put it cd and cd and ascii. Okay, now under this we have We have already downloaded whatever is there. We have unzipped also, basically ML, oh, 1 million we are talking about over here, right? So ML dash 1 million is here, right? So basically in this case, let me just show you what we are talking. So this is a movie lens database. These are the real movie recommendation. And what we are going to do today is build a movie recommendation based on past users movie. Okay, so we know we have 1 million recommendation from lots of users, and what we want to do is we want to give the recommendations to the users, and this is the real data. All right, this is the real data. So we have downloaded this data. This data has got movies. Okay, movies are the movie ID, the movie ID, movie name, and the this is what the genre of the movie, sci-fi, horror, something, right? And it is basically the data is split it by double columns. All right, now we have got movies and we have got ratings. Ratings.dat, not ratings.csv. In ratings it says that, and there is something called users. Okay, now in users you have got user ID, the sex of the individual, the age, and you have got the time, the rating, how much, not rating, this is something else. Okay, and then this one, right? This is timestamp. You can see in the readme what is the format of this data. All right, here. Okay, yeah, so it says user ID, movie ID, rating, and timestamp. Okay, and user ID, gender, age, occupation. There is something called occupation and zip code. All right. So that is the information you have about the movies. And now if you see, so we have got users, we have got movies, and we have got ratings. Ratings contain which user rated which movie, how much. Okay. Now, so first of all, what we need to do is we need to convert our comma separated. We need to convert this file movies.dat movies.dat into, not okay, so ratings. Basically we don't have to do anything with the movies, only we need to prepare ratings.csv in this format, right? If you see tail.cs rating.csv and tail ratings.dat. So what are we going to do? We are going to basically, based on the ratings of various movies in past, we want to prepare a recommendation of the users. All right. Now, so before doing it, we might have to push this data onto HDFS and then start working with Mahout to run it. All right. Now, so we have got this ratings.dat. Instead of colon, all we have to do is substitute that colon with a comma. All right. And also we don't require any other field, only we require the user ID, the product ID, which is a movie ID, and the rating. That's all we require. We don't require the timestamp. All right. And the way it is done is using this. So all right, so we say cat this, and we split this input by colon, double colon, and then we print first, second, and third comma separated values. That's all. And now you have ratings.csv by comma separated. All right. Basically, we did a bit of translation from one form to another. Earlier it was double colon separated, and why we have done it? Because Hadoop expects the inputs. Hadoop's this recommendation algorithm expects you to put user ID, product ID, and ratings in comma separated format. All right. Are you guys with me, Prasanna, Jagannath? We are basically trying to build a recommendation engine. This is a very important chapter. It's a reason these recommendation or these intelligent things are the reasons why Hadoop exists in first place. Now we copy this file, we copy our ratings to Asgiri. All right. Actually, you guys should you know run it the whole example by yourself. Only then you will get a feeling of what is going on. Right. So let me just delete ratings for time being. All right. So that's the old ratings, and I've just moved it. Now I'm copying this rating.csv, which we just prepared out of .dat file by by changing double colon to comma and ignoring the timestamp. All right. Now we have got our file under asgiri folder. Okay, here ratings.csv. Now, out of this, what we are going to do is we are going to put our Java home properly. Okay, E- and then see, and then we run Mahat in this manner. When you are running Mahat, you have to tell few things. First, what is it that you want to do? Okay, this is the first. As we told you that there are four things a Mahat does. This is the first thing you need to do. So we want to say that, hey, we want to generate the item based recommendation. And item based recommendation, there are multiple algorithms. There is Tanimoto coefficient, there are other algorithms, and there is this similarity log like likelihood. Okay, so this is the most popular when we have to do a item based recommendation. And other arguments here are minus I. This is input file which we just uploaded, and this is where we want to get our recommendations. Okay, as giri slash recos. Hmm. So the folder already exists. Okay, and the output directory also exists. So we say Hadoop fs minus ls as giri, and we say that this. All right, what did we do? We said, okay, it's not there. And what is it saying? Is it saying, I don't get it. So is it saying that this temp folder is there? All right, and this index already exists. Okay, and Hadoop minus ls and fs. There, do you see a temp folder? Yep, there is a temp folder, right? So it says that the error I was getting, it says that prepare preference matrix and item ID already exists. So let me just delete TMP folder completely. I say rm minus r. Now everything will be deleted over there. Now we have deleted it. Now let's try to run our algorithm again. So what we are trying to do, based on our ratings.csv, the past one, we are trying to generate the records. All right. All right. So let's just try to run it. So make sure that you run the whole thing by yourself again. And this will give you a good amount of confidence saying that you can run all the things together. You can run an Uzi, you can run an HDFS, you can use Hadoop, and you can use Mahat. All right. And once you are done with this command line, you should watch the video of Uzi once and try to run this thing as a Uzi command line. Like here, we have got where is our here. So you can create a workflow over here and say create my workflow. And the way I have created a text test workflow yesterday, similarly you create your workflow and uh, there should be a streaming job, Java, Pig, and okay, okay. It's not there. You'll have to import an action probably. Okay. And okay, never mind. You first let's first try to do that using command line, and then we can look up. We can see that if we can upload a Mahat file. All right, we'll do that. So for time being, let's just do it manually from the command line. So it's doing a lot of things. It's running things parallelly on multiple nodes, right? As you can see from here. So it will take a little bit of time and then it will be done. Okay. In the meantime, we can actually see Mahat and Uzi. All right. So, so there, what we can do is basically import uh, Uzi job. Okay, and not this way. We'll have to see. Basically, this is nothing but calling Hadoop, right? It is calling MapReduce with a lot of command line argument. If you see, this is under the hood. It's calling the Mahat library. Sorry, a Hadoop library. And this, okay, no, this is not done. There should be a better way. Basically, I would suggest that we'll just create a shell script containing the command, or we can do a Hadoop here and edit workflow, and we can say shell. All right. And when we say shell, we can put our arguments. Name is say Mahat, and here whatever we have here, we'll just put it right now over there, and then we can say this is all right. Now here you can put parameters of your choice. If you want to say add an arguments here, you can put the argument over here, and then it will take that file from the argument instead of hard coding these values. Okay, and then okay, we call it recommender and then save it. All right. Now you can basically run it from here also now. The way it is running here, you can also run it from here. All right. Does it make sense to you? It will do a couple of passes, and once it is done, In the end, you will see the recommendation in this file over here. So from here, you will have to run it using Uzi. Okay, you'll have to run it using Uzi. The way I've just defined over here, you'll have to put this command in the command, and then you have to save it and then run it. All right. Or basically what you have to do is go to workflows, create your fresh workflow, create a shell command, and put this command with your folders, right? Your folders in your directory, and then rerun it. All right. That will be sufficient. Is that okay? Okay, Prasanna? So let's just delete this one and we will run it. I mean, this is the flow which you should be doing. Okay. And it starts, then runs the recommender, it ends. Or in the meantime, the way we did just now, before this process, what we did was we converted the data from one form to another one, right? That also you can put as a step over here. All right. Say we say shell, and then under that we can put all these steps like downloading it, unzipping it, then you know translating this can be one step in Uzi. Okay, and Uzi can run it by when you say submit, or you can say schedule. Okay, whatever you have flow you have made, you can either submit it right away or you can schedule it. So whatever you're doing from command line, you can do it from there also. Right. Now, what is it saying? It says that first attempt failed. Now it is trying again. So if you can see here, this will give you one good idea. So here it was doing something and first attempt failed somewhere. So it did not stop. It tried, it is now scheduling that same mapper on another one. So this is resilience. Okay. This is resilience. For whatever reason, for timeout, for whether it was busy or something else, it has done that. Okay. Now it's doing a lot of churning for you without you knowing about it. The total number of records are 1 million. Okay. And it's doing the churning of that data. And you can see that how big is our file? Our file is how much? If you go to Asgiri and you say 1 million, not this one, not this one, not this one, ratings.csv. Ratings.csv in itself is 11 MB. Each record is 11 bytes, right? And since there are 1 million records, this is close to each record is close to like 13 bytes or so. Okay. Now here, let it be, let it be. So it will take some time, let it run, and we will talk about something else till then. At the end of the process, once that finishes, there will be part 1, part 2, just like our MapReduce jobs. Under that, if you open that file, you will see that for this user 6029, we are recommending 3 movies: 2712, 1358, and 1283. Okay, 2712 with a rating called 5.0, which means this is like highly probable that this person will like 27th movie. I mean this movie. Okay. Similarly, over here, over here, it's highly likely that these people will like all of these movie with the probability of 5.0. They will like so much, and they like 100%. 5.0. If they are asked to rate these movies in future, they will rate them 5. Okay. So that's the kind of output you will get at the end of it. Okay. And once you have generated this output, you will dump it in MySQL or any other database from where your web application, your J2EE application or Django application or any other CGI application will pick up the data and start displaying. Okay, while this job will keep on running in the back end every day, every night, generating these recommendations and pushing it to MySQL, the serving will be done by some other database. Okay, because most of these processes are batch process, these are not live. Now there are other recommendation algorithms such as similarity log likelihood. Oh, it is finished. It has taken 10 minutes, 9.9637 seconds. All right, now it is, let's just say, how do you, okay, so ratings file has been generated on October 26th, and just now you can see, and under this you will see, not this, no, sorry, not this, under records there will be the file. So there is this records folder. The file is created at 9 a.m. GMT probably, and under this you can see the recommendations are there. Do you see the recommendations? Even you have 4.5, you have, so, and and so for the first user these are the 10 movies which we want, right? By default it only gives us 10 10 recommendations. Okay, we can also specify how many recommendations we want. Do we want 5, do we want 2, do we want 3, and all of that can be configured from the command line arguments. All right, so it has generated the whole recommendation for these all 1 million records. Okay, if you go to the last block, is this much. Also you should note that the key is ordered. Okay, key is ordered, this is the value, which signifies that most of it is done through MapReduce. All right, so for 6040 user, this is the recommendation, which means around 6000 users are there in this data, and there are some, maybe, how many, a thousand, a few hundred movies would be there. All right, so this is generated, and now you can see that you did not have to apply any algorithm, you did not have to write too much of code. All you needed to do is format your data into a comma separated values. That is the format which Hadoop, Mahat expects you to do. All right, and it gives out in a nice format which can be handled quite easily. Okay, it's a key and value separated by a tab, and the values are tab separated. Okay, here if you see, the values are tab separated. Here key and value, here this is separated by a tab, and all the values are separated by comma, and then there are further column separated. So this is quite easy to parse. It's quite easy to parse for you. Okay, if you are using a Java API, you do not need to parse it, because it will return you a list of object itself, which you can present in whatever format you want. All right, and as a next step you might have to again churn this data using your pig, and convert it into a format which can be inserted directly into your MySQL. All right, or you can just take this file and move it, copy it to your other server from where you will be serving these recommendations. That's how we were doing earlier. All right, now, so we generated the whole recommendation of 1 million records in 10 minutes. All right, using a cluster of few nodes. Good. These are the other recommender algorithm. We used the first one. You could use the other ones. And the other one is cosine, which is quite popular. I use Tanimoto coefficient based on the kind of similarity I was looking for. I had some more attribute to look for, so I used that one. So you can choose either of these algorithms according to your need for recommender. Similarly, as a if you are really interested in this kind of work, what you can do is you just go through all the algorithms listed under Mahat and then see which one fits to your need. They have done a very good job. They have listed it in a very nice format. And these are the use cases which I have already covered. So congratulations, you have completed Mahat part. Okay, Mahat is a very important aspect. Now, similar to what we have just done, item wise configuration, you have other things you can use. All right. Now, okay. So now we start with something called Apache Spark. Apache Spark. Apache Spark is a fast general search engine for large scale data processing. All right. Now, what does it mean? It means that it is similar to what we had been trying to do using MapReduce. Okay, in MapReduce you had to define key and the values and so on. The life was actually simpler because MapReduce has a very simple and singular construct. There is nothing more than key value pairs, nothing more than MapReduce. Okay, in the MapReduce framework, that was very overly simplified framework. Now researchers realized that MapReduce is not sufficing their need. They could do little better. So they came up with something like Spark. The quality of Spark is that Spark is blazingly fast. Okay, blazingly fast. Whatever pitfalls were there in MapReduce, they try to iron it out, and then build this new framework, which is they claim that in when it's run in memory, it is 100 times faster, and when it run on disk, it is 10 times faster. Okay, but so and it's quite powerful in terms of various aspects, and this is well integrated with Hadoop, and this builds on a similar paradigm as Hadoop. I would also say that whatever we learned during pig, that will come into a very use now, although both the tools pig and Spark are completely unrelated, but the paradigm is similar, and you will understand why I call it similar when I talk about further things. Okay, so Apache Spark stands on top of Yarn, and there is a standalone scheduler like Yarn, and there are mesos also. These are the various components on which Spark can stand upon, right? And mostly people are using it on the top of Yarn because they already have a Yarn cluster. Wherever they have a Hadoop cluster, they have Yarn cluster, and Spark core is basically does most of the jobs. And there are other libraries such as GraphX, mlib, Spark Streaming, and Spark SQL and Shark, just like Hive. Okay, and all of these components, all four of these components, actually use Spark beneath the skin. Just like Pig and Hive are using MapReduce, these libraries are using Spark core. Just like Hadoop, Mahat was using MapReduce beneath the skin, GraphX as well as mlib are using Spark. All right, you will understand it more when we talk about things in detail. All right, so there are few concepts you need to understand. The way we understood, there is something called HDFS on which your MapReduce run. Similarly, you have got something called resilience distributed data set. It's a unified, a symbolic data set for all the nodes running your Spark jobs. If your code is there, code will be talking to a singular interface called RDD. While this RDD will exist parallelly on multiple machines because your code also runs on multiple machines. Okay. So RDD is interesting. RDD is interesting phenomena. RDD is basically a little bit faster layer on top of HDFS. Okay. So RDD has got resilience distributed data set, has got few properties. They can be persisted into the memory. They can be persisted into the disk, and they stay in the memory, which means that all the nodes can access the same data at the same time, right? Can have auto recover from node failures. Since we are talking about a distributed system, say here this singular data set is visible to all the four nodes, one, two, three, four nodes, right? And this RDD is visible to all these nodes. Now, in case any of this node fails, then whatever resilience data set was provided to this will be redistributed amongst the other three. That is the property of resilience data set. Now RDD is can be can be defined of any type, but it does not enforce anything upon you. All right. Any resilience distributed data set supports two kinds of things. First is transformation, other is action. Okay. First is transformation, other is action. And each element of resilience dataset RDD runs across cluster is run through map function. Okay, but I wonder why. All right, so basically here I'm trying to show that here lines, when we are this SC, you can think about Spark connection. So Spark connection is the starting point where you start your any Spark scripting. Okay, so you say, hey Spark, this is my file, please load it, and this is the variable name, right? So this lines is basically your resilience data set. Okay, this lines is your resilience data set, which means lines is going to exist on all the clusters in a divided manner. Okay, lines is going to be existing this variable, but each node will have a different data in the lines variable. Okay, so lines is similar to pig. When we say load this into this variable, exactly in the same way it has also done the same thing, right? So this is where you are preparing a resilience data set. So you created a resilience dataset over a file called data.txt existing in your HDFS. All right. Now, as we talked that under Spark, there could be something called transformation as well as there could be something called actions. Okay. Any operation is either an action or a transformation. All right. So what does it mean by transformation? Transformation is run on each of the nodes. As we talked that resilience dataset is distributed across hundreds of nodes, right? Whenever you apply a transformation on resilience dataset, like lines in our previous case, here lines is our resilience dataset. So lines, similar to line, you can create anything, you can load any data and create your resilience data set, and on top of that resilience data set you can run multiple commands, you can run multiple transformations. Okay, so the diagram is like this. There is something called HDFS from where your variable is loaded, called and that variable is basically resilience data set. Okay, and This is your Spark driver application. This is the commander. This guy is the guy who commanded your Spark and said, this is my resilience dataset. Okay. Any code you write is going to get loaded onto Spark driver application. It is any node in the cluster can act like a Spark driver application. Okay, so you will load your code here and say run my script. So this script is going to talk to system and say create a resilience dataset from this file from hdfs, and then run this transformation. Run this transformation can be a simple example like multiply all the values by 3 and put a, uh, make it square of each value, right? That is transformation, in which case the data will remain on the resilience data set. It doesn't come back or doesn't get printed or stored. All right, you are basically transforming data in place. All right, so here we go. So to run the transformation can be done using a map function like this one. Okay, what does this function do is, just focus on this. It basically returns the length. Okay, so what you have done is, on we had lines, right? Lines was our resilience data set, and on lines what we have done is we have computed the length of each line and saved it there itself. Okay, called into a new resilience data set called line lengths. Line lengths also is a resilience data set and is existing across the cluster, across the cluster, right? And similarly, you can keep on applying the transformation in place and keep on producing a new set of variables by applying transformations, right? And this is all being started by Spark driver application. Does it make sense to you, Prasanna and Jagannath? Great. Now that was about transformations. There are multiple kinds of transformations, starting with the map function. Map function is not like your map function is not like your traditional map function. Okay, traditional as in not in terms of map reduce one. Okay, we'll talk about map reduce one also. Here map is just in place function which takes a singular value, convert into another single value, such as square root, divide by 3, multiplied by 5, add 3 more into this. So those are your map functions. It takes a singular value, applies a new, uh, returns a singular value. Okay, so when you apply a map function, all you are doing is applying a transformation in place, a transformation on top of the existing resilience data set, and creating another data set representing the new value. Okay, it's exactly like applying a filter over there. Okay. Applying basically translating into another one. Okay, similarly you have got one is map basically translates your data into another form. There is filter basically returns a new data set out of the previous values. Say you have got 1000 lines, all you want is all the lines which have a length greater than 30, right? So only those lines will be in your data set. So you remember that we loaded a text file into an lines, which is basically an array of strings, and when we applied a transformation on top of it, we have got line lengths. Now out of these line lengths, we just want to keep the line lengths which are say odd numbers. Okay, now you can do this easily. You can run your whole data set through the function, right? So whatever function pointer you provide here, that function will be executed. the way we had created a function here, new function, and then we created a function and passed that reference of that function to the map, and that function is applied on each value in this line, on lines, right? Similarly, in case of filter, whatever function you provide, new function where my value is greater than 30, it will produce a new data set which is a subset of the main one. All right. Similarly, you have something called flat map. Flat map is actually similar to Hadoop's map reduce map, because one single value can produce multiple key values. Unlike this function here, the first function, map function under Spark, it it creates only one value as a result of transformation of one value. Here it can create any number of values based on a value. That is flat map. So that's the duty of the function you write. Now there is something called group by key, right? So out of once you have transformed, it won't automatically group the items by key the way MapReduce of Hadoop did. MapReduce of Hadoop automatically grouped everything by key. It does not do that, right? It does not do that. So, but before you run your dataset through group by key, make sure to prepare key value pairs. All right. Make sure to prepare key value pairs. Only then it makes sense. Right. So these are four examples, classic examples of transformation at Hadoop at Spark level. You can see more of such functions on the on this documentation page. It has got sample, union, intersection, distinct, group by key, reduce by key, sort by key. So if you see, if you look at these transformation, they are like pig transformation, where you loaded a data that you created the first one. Now the next step is you say filter my records by this condition, or you say iterate is equivalent to map. So that is the transformation we are talking about, right? So this one, from the interaction perspective, you will find that this is very similar to your pig. Okay. Now the next thing, which is the next concept which we need to understand with respect to Spark, is actions. What does an action mean? Action means it brings data back to the Spark driver application. Okay. The way our load function started the process of creating an RDD, an action basically brings back the data to the driver application. If you remember in the pig, the whole process starts only when you say dump, or sorry, when you say, yeah, when you say dump or when you say store, right? Similarly, here also, the moment an action is executed, only then all the transformations are applied. Before that, nothing happens. Whatever filter or map you applied in the previous process, they won't be executed until you execute an action. An action can be such as your store, right? Now Spark has got multiple kind of aggregations. One of them is reduce. Whenever you call reduce, it basically brings all of this data back to the Spark driver application. It's a it's basically an aggregation step. While the transformation does not do any aggregation, it runs the transformation on all the machines individually. While the reduce actually is run on driver application. Okay. Generally, it is run on the driver application, but it can also be run parallelly on all the nodes if the driver application is overly loaded. Alright. Now here you look at it. So the kind of actions it provides is reduce, first of all, a reduce one. Okay. Then count. then collect, then take. Now, we will discuss reduce a little bit later. First, we will discuss something about other functions. Count is basically will count all the records lying on the whole network. If there are 5 nodes and you did some transformation on all 5 nodes, when you say count, it will basically get the counts from each nodes and then sum it up, right? So when you have lines, right? When you say lines dot count, basically it is going to call all the 5 nodes and ask them about the count, okay, and then sum it up and then return you the value, right? So that's one example of an action, because an action interact with all the nodes, while transformation is only happening on a single node, on each node independently, parallelly, right? It's happening in a parallel. Action is like a series thing. When all of it is done, only then you will get a result. While in transformation, the transformation will be running on all the nodes parallelly, without give, without aggregating the data, right? Similarly, collect basically brings all the data back to the driver as an array. So the process started with loading the data into RDD, and process is finished, or the job in the above steps is collected back onto the node where it started from. All right, so driver application is something which does all of this for you. Now take an, okay, return an array with the first n element of data sets. Okay, because your data set is distributed across nodes, you just want first n element, right? And it will give you the first 10 elements, right? Now let's talk about the first function which we have skipped, is called reduce. Reduce is basically very powerful function whenever you have to combine the values together. Like earlier in case of map reduce, in reduce we used to sum up all the values to get the results, right? Similarly here in reduce, you can also do that. The only difference is in this reduce you can only pass a function which is basically cumulative and associated in nature. What does it mean? We'll talk about cumulative and associative in the next example. So this function has got a property that it will take two values only. This function is going to only take two values and then return a summation or return an aggregation of only those two values. Now, your immediate question to me would be, then what's the point? We have 100 nodes in the network. Our data is spread across 100 nodes. If it sums only two values, how is it going to function? Right? The answer is it will keep on taking two values and keep on merging them back until you reach to a singular value. Right? So if you have three values, it will take first two values, then say, and this function, whatever it is, it takes two arguments and returns only one value. All right, that you should remember. So if you have three values a, b, and c, it will operate on a and b first, give a result based on a and b, and let's call that result as d. Now once that process finishes, now you are left with d and c, right? D is a result of a and b, while c is still left. Now when you apply the same function on d and c, you will get a singular value. So no matter how many values are there, you can get the results. Now the problem comes in when we do this kind of operation. We take two values, then apply a function, get a value, then run our function again on the resultant until we converge to a singular value. Does this kind of function, can any function be used in these circumstances? Can average be used? Can average a good aggregate function in case of a spark reduce? Can we, okay, and these functions have got a property called cumulative and associative, which means that I'll show you the cumulative and associative. Describing is does not do the justice, but demonstration will do the justice for you. All right. And if you remember, we were talking in case of Hadoop, right? We were talking about a combiner function. You remember combiner function? Jagannath and Prasanna? Combiner function? Actually, it doesn't display the timestamp, so I don't know whether you said it now or earlier. Okay, so in combiner function was exactly the same way. Combiner function was taking two values and then returning it. And in case you have studied a mechanism of sorting called merge sort or divide and conquer, they all function exactly in the same fashion. Merge sort takes two values and then find the minimum of those two, and then it takes another two values and keep on doing it again and again until you're left with one value. All right, and that's how you can find the minimum value out of unsorted values, right? So let me just take you through an example of what is going on. Okay, can you see my screen? All right, so on a single node, on a singular node, we had lines. Then we loaded these lines, computed an array of line lengths, and then we did a sum of all line lengths. How much is the value? Can somebody tell me quickly? 62, right? And if you do say min, right? Min will always be 4 and max will always be, min will always be 4 and max will always be 20 out of this. And sum is 62, right? Good. So this is on the single node. What we did was, basically, if you have to program it without any Spark or anything, you are given a lot array of lines. You computed line lengths. Now you are summing up the lengths, right? Now similarly, now think about multiple nodes. What is going on? You have got first node. Let's think about the problems individual node is facing. So first node, say out of these all lines, first node only got section of it, right? That's how this whole resilience dataset operates, right? So first node only got this value, this value, and this value. First three values, right? Now we computed line length. This got line length is basically each line has got a length 1 2 3 4 5 6 7 8 9 10, and I think one new line is also there, 3 plus 4 7, and then end of the line. So and Giri is let's just say that it is 4 for time being. Okay, why? Okay, you can I mean there is a, I think there is a minor mistake over here in numbers in computing, but never mind. Okay, so let's say ki Sandeep space Giri has got a length of 9 and this has got a length of 11 and so on, right? Now when you compute the total length on each of the nodes, right? So your computation of total length is being done by a reduce function, right? A reduce function. So the reduce function on each node will first convert first two values, sum up two values into 20, and then they take the two values and then convert it into 24, right? So as per node 1, the length it was given to it is 24, right? Similarly, on the node 2, there is only one line and it is 14. On node number 3, right, it has got these two values and line length is this, total length is this. Now, on the driver node will ask all the three nodes, because driver node is the one who told each node to run the reduce function and compute total length, and now it will get the total length from each one, 24, 14 and 24 again, and then it will run the reduce function again on these two values, and you'll get these 38, and then it will sum up these three values, these two values, and you'll get 64, right? Now my question to you is that let's say that we have got we have got this in a different order, right? We have got, say, let's say this. If you sum it up, if you sum it up, will the sum these two values first, and then these two values, and then these two values in whatever, okay, let me just put brackets, okay, that will be better. These two values first, then these two values first, and then these two values, and after doing that, sorry, these two values, right? I think this will make you more comfortable, right? Does it look very ugly, right? So if you sum up these two values and these two values, you will get one value here, and then you'll get these two values. Now when you sum it up, you'll still get 62, right? Now if you change this to 4 and this to 20, right, will the value be same if you sum it up? Great. Now let's take a different case. Perfect. Perfect. So now let's take a different. So that means if you switch these values from one place to another, or you place brackets different way, or you, or in another word, you can say that you are applying reduce function on different values. Will it, if no matter in what order, no matter in what order you are picking up those two elements, you get the same output, then that function is that function is cumulative and associative, right? Now my question to you is average function cumulative and associative? Let's take a case, okay? Let's take 2, 3, 4. All right. Now average of 2 and 3 is 2.5, and then we have got 4. Now average of 2.5 and 4 is 6.5 divided by 3.25, right? Now if you do it other way, right? Let's take a case of 4 and 3, 6 and 3, and answer is 4.5, right? So 2 plus 3 plus 4 divided by 3, average is 3, right? If you do it all together, while the average of these three is this, but if you're doing it this way, the average of 2 and 3, 2.5, and then on so on, right? So the answer is incorrect. So you got it right. It is not associative, it is cumulative. Perfect. Now let's take another example. Another example. A function which is defined at function f of x and y is defined at square root of x square plus y square, right? Is it cumulative and associative, this f function? Let's say x, y, and z are there, and we take x and y first, all right, and we return something like square root of x into x plus y into y, and then z. And the next step, we say we take this value, multiply by itself, and we have got x plus y into y plus z into z, and then sqr root of this one. So no matter in what order do you do this, you will always get this result. Okay, whether you do it all three at a time or two at a time, you'll get always the same result. So it is cumulative as well as associative. All right, so this can be a valid reduce function. Okay, this is a valid reduce function, because no matter in what no matter in what order do you apply this function, on which two values first or which two values last, you are, or you're going to apply the same function on the result as well, you will always get the same value no matter what. All right, Prasanna, do you agree? No? Okay, okay. Okay, so give it a try, give it a try, and I would be more than happy to be proven wrong, right? And I would, also evaluate it again. Maybe I'm making mistake somewhere. Great. Now let me just. So was I able to explain what kind of reduce function are appropriate? Great, great. Because I'm actually very much worried about the approach I'm taking here, right? Now we talked about something called a reduce, as well as we talked about something called other functions, right? So transformations, actions. So transformations basically happen on the same node, and actions bring accumulate the data. And actions are various kinds of actions: reduce, count, collect, take. And this was the example we followed. And we will talk about something called broadcast memory. Okay, basically broadcast variables. All right. So I want to take a break desperately, and let's meet after 10 minutes. Let's meet at 10:25 p.m. IST. All right. In 10 minutes. Hi guys, I'm also back. Should I start? Prasanna, should I start? Oh, okay. Okay. If you want, you can take a bit of time. That's not an issue. And I'll just grab a water bottle. All right. So, yeah. Okay. So now let's continue with where we left off. So, other than transformation and other than actions, Spark also provides you something called broadcast variables. Broadcast variables are really interesting in the nature that that they serve as a common cache for all the four or all the nodes. Okay, and they work as also like if you had used multiple threads, and in the thread.notify, in the similar way we can do a broadcast. All right. So before you start the whole all the nodes, or even after starting the node, you can broadcast a value. Okay. So if you say your broadcast variable is this sc.broadcast new int 123, you'll get this class variable called broadcast var, and whenever you get the value from it, okay, whenever you get the value, you will get the latest value out of it. Okay. Now every time if you are again broadcasting a new set of value, then all the people who are listening to broadcast var.value like this, they will get the latest value uh, instead of creating a new value. If you again do sc.broadcast, then only the people who will listen to the other variable which you create a fresh one, only those ones will get the new value. Here here you, when you created a broadcast variable, you if you use the same variable again and again, you will be able to broadcast your value. All right. Now broadcast is one such important stuff where you can same value, if say there is on rdd1, if you want to update all the nodes with the newer value, then you can just say broadcast my value, and all of those all of those Spark applications will get the fresh value. Okay. And that happens really blazingly fast, in the sense that the broadcast variable is basically serves as a common cache for the whole Spark application. All right. Now, all the application, all the nodes, this each individual node, Spark nodes, will get the same value, and either of them can broadcast, so all of the other nodes will keep on getting informed. Okay. So this happens really really fast. All right. Now this is a way of communication between various nodes, and this works pretty well in lots of cases. All right. Now one way of communicating between other nodes is using broadcast variable, and the other way of communicating back is using accumulators. Accumulator does not communicate using accumulator. These nodes do not communicate between themselves, but they communicate back to a central storage, right? So 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 basically you define an accumulator over your Spark connection, and this accumulator keeps on pushing the value into it. So okay, so each node can push a value into accumulator but cannot read you cannot read a previous value. Okay, you can only push to it or read the current value. It's a single variable, remember, it's a single variable. Okay. So it's like you keep on pushing a value to it, it keeps on adding or say concatenating, and at the end of it you will have a you will have the same value by virtue of all these additions, right? So all of these, they, because accumulator do not suffer from classic multiple threading problem, because all they have to do is add these values. So whether 10 comes first or 20 comes first, the at the end of it the result is going to be same. Okay, therefore accumulator does not suffer from these kind of values. Okay, and these are very useful properties, these are very very useful way of communicating, because these are unidirectional. It's only from node to the central storage, it's not by both the directions, right? So this makes so there is an accumulator and there is a broadcast variable. Broadcast variables are great if nodes want to communicate with each other, and accumulators are great if they all want to publish a statistics to a central place. Okay, say you want to show that you want to show that these are the records that have been published so far by all the nodes we have. Okay, you are running a big cluster and you want to show that what are the all nodes that have been pushed so far, right? Now, so how many records have been processed so far? If you want to publish it, it's pretty simple. Each Spark application can just push number of records to an accumulator, and then accumulator you keep on showing it to the user saying these many records have been published. So accumulators are very very useful in that sense. Okay, they help you do a really really fast way of computation. All right, now we have got something called Spark streaming. Oh, what happened? So that was pretty much with respect to Spark, and that was pretty much with respect to Spark. So Spark has got transformations and actions. There are multiple kinds of transformations and actions, and then there is something called broadcast variables, which is good for broadcasting. Then other concept you need to know is accumulator, and that's pretty much it. Okay, you should, I mean, give it a try. All right. We have not been able to set up a Spark onto our cluster yet, but we are in process of setting up a Spark on the cluster. Then you can try it out. All right. Now, as we saw that all the nodes are able to communicate with each other using a broadcast variable. That and it's really really fast to process the data on Spark. It makes a good case. It makes a good case to do the streaming. Streaming means processing the time-bound data in a really, really fast manner. That is that is the Spark streaming. So Spark streaming can happen from various kinds of queues such as Kafka, 0MQ, or data sources such as Twitter, SDFS, or maybe Flume. Flume will read from Apache logs. And we covered Flume yesterday. And this basically means that Spark streaming will read the data from these fast-paced data sources and then show it to the dashboards. That is the role of Spark streaming. Spark streaming is basically a library which sits on top of Spark and provides you the function which is required in the streaming streaming applications. All right. So this is okay. Now, and when we talk about Spark streaming, it's nothing but It's not an additional component. Remember, it's not an additional service which is running. It's only additional API which under the hood calls the usual Spark API. But this API is called, has a class called dStream or discretized stream. Okay. So discretized stream as in a window by window operations of a continuous stream of data. So we have got input data stream coming to Spark, batches of inputs of created and is given to Spark engine. Okay, and batches of the data is processed batch wise in a small window. Okay, so if you look at it, even if we call it a Spark streaming, under the hood it does the things in batches, or we call it a time window. All right, and that is quite, I mean, interesting idea, because when people think about streaming, they think that we are going to process one record at a time. But the truth is, that never happens. We always consider our time window, no matter how fast is our data coming. Right now, so Spark streaming basically receives the live input data from various places, divides the data into batches, and then Spark engine generates the final stream of results. So here, whatever batches you prepare, you ask the Spark engine to load the way we loaded the files, and then it will process the data. Okay. Now you can see this. Internally, internally a D stream, though D stream looks like a flow of the data, you keep on adding the data into the queue, keep on taking it out. D streams looks like a full-fledged pipe kind of structure in API perspective. But under the hood, it stores in a resilience data set. Okay, a resilience data set has the data from uh, on various time windows, right? So node 1 will have, say, the data from 0 to 1 second, and node 2 will have, say, data from 1 to 2 second. Node 3 will have 2 to 3. Node 4 might have 3 to 4. Okay, this is completely up to you how do you define it, or how do you push the data. Or you can think of it this way, that RDD, the key of the data is microsecond. Okay, and that's how this is organized. Now you always create the window operation on any D stream. So D stream has got something, and then you reduce by key and window. Okay, reduce by key and a window, meaning the key is the time here, and your reduce function is going to get applied on a window, which means basically a range of keys will be ap- affected by your reduce function. Okay, and those are the window operation being provided by dstream class. All right, so this is how it happens. So it creates windows of time and then applies on that. Right, now let's take a simple example that will make it more clear to you. How does it happen? So first and foremost, when you are dealing with Spark streaming, you create something called Java streaming context. Okay, Java streaming context has got a name and a process name and the duration at which the data has to be read. Okay, so here we have said 1000 millisecond, which is 1 second, and we are saying Java receiver input D stream, and what we have done is we have created a connection, a socket to this particular port. Okay, we are opening a port here, we are reading the data from here. All right, now whatever data you read here, right? So Java streaming context is a class provided by Spark where you keep on reading the data from local host and this particular port and this particular host at a duration of 1000 millisecond. Okay, every 1000 millisecond it is going to read the data and dump it in lines. Okay, dump it in this variable as an array. It looks like an array. Okay, it's a stream of strings coming from this particular host. Okay, every 1 second. Now whatever lines you have read here, you applied a flat map. Flat map is exactly like your map reduces map, where you went over this string, splitted this string by space. You are counting words. Remember, the overall objective is counting words in every window of 1 second, right? So you can do the word count every 1 second. That is the objective. Okay. So here lines contains the strings read every second. Okay, or you can think of that total number of lines which have been read so far is this much, right? Now what you do is you iterate over the lines. Okay, you iterate over the lines, and then you split the value and convert that into a arrays of words. Okay, now you got a set of words every second. The words which have been received per second, they could be 1000, they could be million, they could be 100, they could be 50. Okay, that complexity is being handled by your resilience data set, which is lines as well as which is words. Okay, now we read, these are the words which are basically read per second from the input source, which is localhost 49s, right? Now we got these words in place. Now on words we can apply a map. Okay, on these words we can simply apply a map so that we can have distinct words per second. Okay. The word count problem in which we were counting distinct words earlier in the whole file, here we are counting the distinct words per second. Okay, now all we did over here is called a function of creating tuples. We created tuples over here. Okay, and tuples contain the word itself and a numeric one. So basically this thing converted a list of words into a list of word and a number, which is 1. Okay, and that combination of a word and a number 1 is called a tuple. So we can say that from a list of words we have converted into a list of tuples, and each tuple contains the word and the number, the count of that word, and right now which is 1. Now once we have generated these pairs of key value pairs, word and numeric 1, now we can do a reduce by key, just like our reduce. And reduce by key, because we have defined a key in this phase when we did a map, right? Now reduce by key will simply some add these values and we get the word counts. Okay, so basically this whole process is printing the word count every second as and when they are happening. Okay, so lines from D stream, from time, lines from 0 to 1, lines from 1 to 2, lines from 2 to 3, they will convert it into words from time to 0. Okay, these are the operations which are happening in the previous screens. And at the end of it, you will get the total distinct word every second. Was I able to make sense, or did I skim something? So basically the only benefit this guy Spark Streaming has provided you is this, called JSSE, this stream. Okay, this is what is provided by Spark Streaming API. Rest is exactly same. So do you want me to explain something which I have covered so far? Okay, great. Right? So instead of operating on whole file, we are just operating on a data captured by the D stream every second. That's all. All right, great. Now there is another contender for Apache, which is called Apache Storm, and Apache Storm is a little older system, and you also can say it in a better word that it is more experienced than our uh, Spark streaming. Okay, so Spark streaming is I mean Apache Storm is has been basically there even before the Hadoop days. Okay, and it runs independent of Hadoop in general. Okay, and it basically benchmarks it to 1 million tuples per second per node. Okay, it's extremely fault tolerant and scalable. So there are many people who are using Apache Storm, and it is you know used in real-time analytics at a very large scale. Okay, and it is for continuous computation all the time. And Apache Storm can very well be used in machine learning, online machine learning, where you require a very fast turnaround time. All right, and it can also be used for ETL. Now these are the comparisons of Storm versus Spark streaming, where in case of Storm, the processing model is record per at a time. Each record is handled at a time. In Spark streaming, as we just did, there was a mini batch as in 1 milliseconds batch, right? The latency of a storm is less than a second, while in case of Spark streaming, the latency is around few seconds. Latency means the total turnaround time for a call. If you make a call to Spark streaming, it might take a few seconds. Fault tolerance, in case of a storm, there may be duplicates, okay, and in case of Spark streaming, basically Spark streaming is less fault tolerant than Storm, right? Because in case of Spark streaming, the window which we are picking up, they are non-overlapping windows, okay, and therefore the record will only be once. But in case of Storm, because it doesn't consider a window, a same record might be processed twice. But when it comes to streaming or any of these fast moving systems, a minor fault such as processing a data twice is better than skipping any data. Okay, and implementation and programming API is Storm was done at Twitter and Backtype, while Spark streaming was done at UC Berkeley, and these are the other comparisons. Now, with respect to production support, Storm is being was used with the Twitter since 2011 and others, while Spark has been since 2013. Okay, and these are the distributions which cover it. And the resource manager integration, Storm doesn't require yarn, but Storm doesn't require mesos, but sorry, Storm runs on mesos while Spark runs on Yarn as well as mesos. Okay, mesos is similar to Yarn. So in very simple words, Storm basically is far more stable than Spark, but Spark has a dedicated company supporting it. Second, it is compatible with Yarn. If your data is already coming via Flume, via HDFS to your Yarn, then it makes sense to have Spark streaming in place. All right. So that was a very brief introduction about Spark. Okay. And Spark basically runs independently on all the machines, and whenever there's a queue, it gets spread out all to all nodes, and they keep on functioning. Okay, all right. So that is, the roughly everything about Storm and Spark comparison, and you can also read more blogs about these. And now I wanted to discuss a few things. Like it's a very so now we are done with Storm, Spark, Mahoth, and I'm moving on to comparing all the NoSQLs. Okay, comparing NoSQLs has got a greater importance because as an architect, you will face a lot of design choices while picking up one database over another database. All right, so now here you will have good. Now, first NoSQL database I want to discuss is Redis. When somebody, generally you need to build a sort of an instinct when we talk about databases and when we talk about architectures. So when somebody tells me that this is going to be on Redis, okay, what does it mean to me? Or should we do this on Redis? Okay, so what does it mean? Basically, Redis is an in-memory database. Okay, although the data is supported onto the physical file, but Redis need to keep all the data into the memory. Okay, if you have 50 GB data, then that simply means that you require 50 GB RAM. If you are using Redis, it won't run on a system where your RAM is smaller. Okay, so that is what Redis is. But Redis is heavily tuned, and the purpose of Redis to exist is extremely blazingly fast computation, because nobody is reading from the disk, you're only reading from the memory. And also Redis can function in conjunction with other Redis servers, which means if you have three machines having good RAM, you can run Redis on them, and it can still function very well. So if you have for kind of not too big data, it is not in terabytes, it in gigabytes, 100 giga, if you can afford that much of RAM as compared to your data, then you should go for Redis. Okay, and if you have to basically churn your data really fast, such as computing statistics and in the games where distributing onto MapReduce is not possible, in those cases Redis comes as a big savior. Okay, so whatever results, say for example our recommendation is being run continuously. Okay, so you might have Redis in between to serve these recommendations to end user, so that recommendation display doesn't take less than milliseconds, right? Because whenever somebody fetches from Redis, it will be really fast. But computing a recommendation using Redis will be extremely difficult, because if you are churning few terabytes of data, you don't have that bigger RAM, and therefore NoSQL doesn't, I mean, this Redis will not be much helpful to you, right? Now, so that was about Redis. Redis is simply, in simple words, in-memory database, which means can hold smaller memory, but can have a greater, I mean, can have a very fast turnaround time. Now, MongoDB. MongoDB, in simple words, in three phrase, in a single phrase, it is document-oriented database, right? In other session, I had been teaching both the things, Redis and MongoDB, to two people. And MongoDB is basically for the cases when your objects which you want to process are complex. All right. So MongoDB is quite a useful tool even in the cases where your data is smaller but you want a faster turnaround time. So MongoDB tries to utilize maximum amount of RAM available onto your machine in order to serve extremely fast. Okay. And basically this is great in case you want to basically publish objects to the end user. All right. Because in case you have tables and joining tables is taking too much time, which is not acceptable by the end user, you will have to convert those tables into objects so that you don't have to keep on computing again and again those objects. Instead, you just store those objects. Okay. And this is quite a useful database. And right. So document, when your objects are complex and constructing your objects takes a bit of time, in those cases you would prefer using MongoDB. All right, MongoDB independent database and similar like Redis. Now Cassandra is very similar to HBase, as well as it provides a almost SQL-like interface to an extent that there is an ORM layer for Cassandra. A ORM layer is called Hector. So in case you have a need of a relational like database, but your throughput demands are higher, or the data size you want to store is in terabytes, hundreds of terabytes, then you might prefer either Cassandra or HBase. Okay, and these are the other examples. I mean, right? Now HBase is basically in simple word like Cassandra. It's just that it would require you to have a Hadoop HDFS in place. Cassandra doesn't require an HDFS in place. Okay, so HBase is more heavy lifting guy as compared to Cassandra, a little more than Cassandra, just that it requires you to install HDFS and Hadoop in general. Okay, in case you don't have that stack, you might hesitate using HBase a bit. Instead, you might opt for Cassandra. Okay, so similar to HBase, and same as HBase, you have Hypertable, Accumulo, as well as Cassandra. Okay. So these are three, four main databases which people use: Redis, in-memory database; MongoDB, document-oriented database; Cassandra, almost SQL. While HBase is there are billions of rows and millions of columns. Now, with respect to project, I want to discuss it with your all teammates, right? In the meantime, the way our projects, the way we assign projects to the teams is is based on your choice. Okay, you come up, I will drop an email to all of you with asking for what kind of project do you want. You introduce yourself again to whole team and then pitch in that this is the kind of project we want to do. In case you have not decided, then you might join anybody else in the team. Okay, we form a group of three. So in this group we have like 7 8 members. Okay, so we can form two groups and then we can start working. All right. All right, so this is generally the submission plan we have. Okay, so confirmation of the project you need to do as early as possible. Okay, and then I'll be requesting a update next Saturday. Okay, and we'll have a meeting, or we can have a meeting on Thursday. Let's have a meeting on next Saturday. In the meantime, we'll have all the conversation on email. I'll be assigning the project, and then you can start your work. Okay, I'll you will be giving me a name for your team, and then we'll be creating accounts for your teams, and then your team will be downloading data and putting it onto the server, and then we'll also in the meantime I'll do a planning of the resources which you require. Right now we have enough of the cluster, but we can add more nodes if required. All right, because there are other teams who are working, and we'll be dispatching certificate soon after this, and the certificate is in the process. So right now, if you have not finished your project, your assignments, please finish all of the assignments by next Saturday. Okay, next Saturday you should finish and close the chapter of the assignments. All right, so this is what it is on a large scale. Go through the publicly available data sets. If you get an idea, okay, if you get an idea, it will be great. Otherwise, I'll recommend you some project. All right, and we will be having at least two meetings for this project, and we should wind up within 2 weeks. Okay, we should wind it up by 8th of November. All right, so in 14 days we should close this project whatever we start today. So that's pretty much about the course, and thank you for attending the course, and let's work on building a nice product or the project as part of this 14 days. In case you wish to work on a larger project, let me know. We will have a larger project for you. All right? Prasanna Jagannath. So that's pretty much from my side. If you have any questions, you can ask. All right. So thank you, Prasanna, and thank you, Jagannath. Bye bye. Have a great day. I'll be sending the email to all the team members by morning, and then you guys and introduce yourself and then describe the kind of project you want to do. In the meantime, go through this list. Where can I find the large data set? I'll be uploading this presentation immediately after this session within 5 minutes, and and then you can have a look at this presentation and start working. All right. Thank you, Jagannath. Thank you, Prasanna, and have a great day ahead. All right. So I will take a break here. If you have any questions, you can ask. Otherwise, we can take a break now. Should we take a break? Should we close it now? Okay. Okay. Great. So let's stick with the timelines, these timelines, and We'll have another meeting maybe in the midweek for half an hour just to get an update of how is it going, how the projects are going. In the meantime, I'll drop an email to all the people, and then we'll decide upon a project for each team, form the teams, and then work towards closing those projects. Okay. Bye bye. Have a great day.